Hello and welcome to lecture number 15. So today we are going to learn the microemulsion phases in somewhat more detail. So if we start with the textbook definition of microemulsion, so it says something that it is a single optically isotropic and thermodynamically stable liquid phase which is formed when oil, water and amphiphile means surfactants are mixed with each other in appropriate amount. Alright, so the most distinct feature is it gives a single and optically isotropic. That means if we do some optical analysis, we will only see a uniform phase. That means a single uniform phase, which is also thermodynamically stable, that which we have already discussed in the earlier lecture. So the question is, can we describe this microemulsion by some alternate phrases like small scale emulsion? So can it be defined as small scale emulsion? So let's take a look. So as we have already discussed that for emulsion we need oil and water. So mixture of oil and water, if we don't have anything, then the two substances exist as phase separated systems. So then we had two options. So either we add surfactants or amphiphile in appropriate amount, right, in proper conditions, right? And also we can have the mechanical agitation, that means stirring. So what we see in both these two cases, so here we don't add surfactant and here we add surfactant. So when we add surfactants, so we form a spontaneous single optically isotropic phase, and this phase optically also found to be translucent. Okay, that means it appears very clear. So and on the other hand, if I don't have surfactant, if we just add just do mechanical agitation, we will also form a non-spontaneous phase, but this would be like it would have some milky appearance, means opaque. Okay, and obviously in general means this phase is thermodynamically not stable, so it is also known as metastable. And this one is thermodynamically most stable. All right, so thermodynamically stable. So what we see that in general, if we add surfactants in proper conditions in an oil and water system, we will spontaneously form a translucent single isotropic thermodynamically stable phase, and that is nothing but called microemulsion. So in other words, when conditions are right, microemulsions are formed spontaneously. We don't need mechanical stirring. On the other hand, the other phase that we are getting, this is also single phase, but it needs some mechanical agitation, and it would have a milky or opaque appearance, and it is metastable. So the moment we stop mechanical agitation, it would go back to the, it would become phase separated. So ideally that phase which is metastable is also called emulsion. And so remember, using mechanical beating, you don't get particles like droplets as nanometer dimension. So whenever the microemulsions are formed, what we usually see, that these droplet sizes, the emulsion droplet sizes, are between somewhat around 10 to 100 nanometer, and in some literatures they are described as even smaller, 5 to 50 nanometer. So nonetheless, the microemulsions are only formed when the droplet size fall below 100 nanometers. So that means they are very tiny, very small. But here, interestingly, these microemulsions form spontaneously in presence of surfactant, but with mechanical beating, you can have droplets so small. So here our droplet sizes are more than 100 nanometer, basically in micron sizes. So when we stop beating, it would go back to the phase separated state. All right. So that's emulsion, and this is microemulsion. So therefore, we simply cannot call microemulsion as small scale emulsion. So no, this is not an appropriate description. So there is some differences and some major differences that we can understand between emulsion and microemulsion. All right. So now we have a clear idea about the definitions. So now let's go back a little bit. That is historically when and how this microemulsion term was introduced. So there was an interesting story behind it. So I'm going to erase the board, and I'd like to tell you that small story. All right. So let's do it. So the microemulsion term scientifically was first introduced in 1950s. All right, and the term microemulsion is also sometimes referred as micellar solution or even Solon micelles. All right. So why this microemulsion is connected with this micellar structure or micelles, that we will come, a bit later during today's lecture. But before that, there is some interesting facts about the microemulsion I would like to share with you. So although the scientific research involving microemulsion started from 1938 or 1940s, but it is believed that the use of microemulsion was in practice long ago. So probably the first practical application of microemulsion was carried out in early 20th century, and it was known that somewhere in Australia, a group of people used to clean wool with the help of formation of microemulsion, and it was known that this group of people are actually Australian housewives, and they developed a homemade recipe for cleaning wool. So what they used to do it is they used to make a uniform mixture using water and eucalyptus oil plus they used to have soap flakes plus they used to add some white spirit. Okay, so as you understand, spirit means alcohol. So white spirit, most likely they were using vodka, and using all four components, they used to make a translucent single phase mixture, almost like a solution. With that, they were able to clean the wools quite effectively. So this mixture is known to be the first, the practical application of, or the first documentation of forming a microemulsion. All right. So now let's take a look at the composition here. So here we have water, oil, soap flakes, but interestingly some white spirit came. So why does that come? So now when the research got developed, so people noticed that for forming microemulsion, if you are taking SDS, sodium dodecyl sulfate, as the emulsifier, means the emulsifying agent, that means as surfactant, then you would only form effective microemulsion if you add with SDS some kind of aliphatic alcohol. All right. So this was experimentally verified. So you see how accurate those Australian housewives were making the correct composition. So the eucalyptus oil was actually the source of oil. That means the non-polar solvent. All right, the having this hydrophobic layer. Soflakes usually have the SDS, sodium dodecyl sulfate, and the white spirit or vodka they used to add that's actually the source of aliphatic alcohol. All right, so this was the little story of how these microemulsion came into use. So next we are trying to we will be trying to answer the one fundamental question that I asked you long before when I tried to talk about micelles and micellar structure. So the question is, if I have a oil and water mixture, okay, and if I slowly add, so the question here once again, if I had water and oil, a mixture, and to it now I am trying to add dropwise some surfactant. So the question is, what would we expect? A micelle formation or what? In what medium? So we are now trying to address that question in a very systematic manner. So let's clean the board and try to address that question here. So here we are. So I'm back again with the same question. So we have a phase separated oil and water system. Now if suppose we are adding the surfactant or the amphiphile dropwise, and we are keeping on adding it. The question is, what do you expect to happen, right? So from our understanding of the surfactants, micelles, and this surface tension or interfacial tension, that now very well, if we imagine about the microscopic picture, so we can understand that the surfactant is described something like this. It has a polar head group and a non-polar hydrocarbon tail. So therefore, what would happen that at the beginning, these surfactants would try to get absorbed at the interfaces of the oil and water. So therefore, it would tend to bury its polar head group inside the aqueous medium and the tail inside the oil medium. All right. So this should be thermodynamically most preferable orientation. All right, and we have seen it earlier. But the question is, what would happen if we keep on adding the surfactant, and as we keep on adding the surfactant, the interfacial tension relapses, means it relaxes, and this interface expands, and we keep on accommodating the added surfactants. But how long? Means there is a limit when there will be no more space available where the interface would be unable to expand anymore. Yet, what I'm trying to say that in this form, like oil on top, water at bottom, in this arrangement, there is a limit that interface can expand to up to a certain point. So if we keep on adding more surfactant, what would happen? All right. So what the question is, would the added surfactants would make a normal micelle in aqueous phase, or they would make an inverted micelle in the oil phase, or the surfactant would stay as a phase separated medium. Alright, so there are many possibilities. But the likely outcome, so the likely outcome, what we can say, that if we think about the thermodynamics, the most preferred area or most preferred location for the surfactant interface. So how about if we can increase this interfacial area infinitely high? And what is the way to increase the interfacial area infinitely high? By having some tiny and tiny liquid droplets, okay, with nanometer size. So that means a nanometer size droplets. If we can produce a billion of nanometer size droplets from a surface from an interfacial portion like there, we can form an enormous amount of interfacial area. So if we can produce an enormous interfacial area, we can easily accommodate those surfactant. And so therefore, it is only possible if we can form microemulsion. So definitely the answer to this question is the formation of microemulsion, and this is most likely. Why I am saying most likely? Because this is in general. Alright. So what kind of microemulsion would be formed? So either it can form oil in water microemulsion, or it can form water in oil microemulsion. So whether it would be the first type or second type, it would be governed by the surfactant type. So what kind of surfactant we are adding, is ionic, non-ionic, and some conditions, some specific conditions. So the condition means, the concentration of the surfactant is one issue, and the second is whether we would be adding some other like aliphatic alcohol, or we'll be adding some electrolytes, or we would be changing the temperature. All right. So anyway, if you remember our definition of the microemulsion when we started, that it's a assembly, means it's a phase consisting of water, oil, and amphiphile. So the word amphiphile consists of both, means surfactant, and if we can add some aliphatic alcohol also, that alcohol, it is implied that the surfactant and the alcohol together means the emulsifying agent, whatever they can form, these two together form an emulsifying agent, and that is known as amphiphile. So therefore, the question is how to predict. So how to predict which type of microemulsion would form and when. All right. So these different types of microemulsion and its formation has been predicted by the researcher Windsor, and he predicted 4 different types of systems can be produced, and we call these as Windsor systems, and also known as phase equilibria, because whatever phases will be formed, they will be in equilibrium with each other. So these Windsor systems or Windsor phase equilibria is able to predict the different types of microemulsion phases that are formed when surfactants are added to a mixture of oil and water. So now let's take a look that what are these 4 different Windsor systems of microemulsions. So I'm going to describe the types one by one on the board. All right. So let me erase it and let me start it from here. Okay. So here with some flow chart, I'm trying to describe the formation of Windsor systems or different phase equilibria as predicted by Windsor. So we start with a mixture of oil and water, water at the bottom, oil is floating above, and we are adding surfactant. So when we have added sufficient amount of surfactant, so there is a possibility that we may form this scenario where the possibility means it depends on the condition, and the condition is the surfactant that I have chosen is such that it is preferably soluble in water. Okay, so that means it could be some ionic surfactant and with a larger polar head group. So it likes to go to the water phase. So whenever we have that, we have a formation of microemulsion phase, and this is how it forms. So there would be a formation of oil in water microemulsion, and it would stay at the bottom. So there would be, we can see two different phases. Alright, so we can write here two phases. So it's a two-phase system. And what are the two phases? That is the excess oil on top and the microemulsion phase. So here, the microemulsion phase will be surfactant rich because it would have quite a lot amount of surfactant. And the excess oil phase would be surfactant poor because there will be very small concentration of the surfactant. But the most interesting point is that the surfactant would only form the self-assembly or whatever in the microemulsion phase. It won't form a micelle in the excess oil phase. So surfactants would exist essentially as monomers in the excess oil medium. And such type is known as type 1 Windsor system. Remember that here we have oil in water microemulsion. Alright. So next we try to describe the type 2 Windsor system. Okay, so we move on to the second type, where obviously everything opposite happens. So therefore, if the surfactant I have taken is preferably soluble in oil phase, then most of the surfactants are in the oil medium. So therefore, we'll have a formation of microemulsion in water in oil system. So that part would stay on top layer. So stay as a top layer. The surfactant rich layer would be the top layer as water in oil microemulsion. And the bottom, we have the surfactant poor layer consisting of excess water. Okay, and once again, there will be very few surfactants present as monomers in the water medium. So this type also has two phases, 1 and 2, and this is known as type 2. But at this point, I would like to emphasize that the reason it's called phase equilibria because the microemulsion layer is in equilibrium with the water layer. Or here the microemulsion layer is in equilibrium with the excess oil. So that means the surfactants actually they come from the microemulsion to oil medium and then come back from oil or water, pure water layer, pure oil layer to the microemulsion. So that's how there has been an establishment of phase equilibria. All right. So now we move on to the third type. So in the third type, depending on the nature of the surfactant or the conditions, a situation arises when there will be both the surfactant poor oil layer existing as the top surface, the top layer, or the surfactant poor water layer existing as the bottommost layer, and in the middle there will be a special phase, and that phase is called the middle phase microemulsion. So between the two, here is the microemulsion phase, and this microemulsion phase denoted as M. M stands for the middle layer, middle microemulsion layer. So this layer is in equilibrium both with the oil as well as the water layer. Alright, so one of the most characteristic feature of this type 3 is the middle layer that is formed is mostly, it gives rise to a bicontinuous phase. And if you wonder what is a bicontinuous phase, then please refer to the structure of micelles, the lecture where I described the different structural aspects of micelle. There I described the bicontinuous phase. So therefore, this type is known as the type 3 Windsor system. Alright, so next we move on to the last type, which is type 4. Now in the fourth type, a very interesting situation happens. So here we have a single phase optically isotropic micellar solution, and this is completely uniform and translucent, and it appears almost a pure solution. And most importantly, there is one single phase, so that is called the type 4 Windsor system. So the question is, whenever we are talking about micellar solution, that means that some micelles are formed. So are those normal micelles or inverted micelles or something else? That would solely depend on the choice of the surfactant and the conditions of the amplifier. So, but one special aspect of this type of single phase micellar solution is that for this type 4 to happen with surfactant, so we have to add some aliphatic alcohol. Alright, so together it forms amphiphile. So we have to have the sufficient concentration of amphiphile, that means surfactants, if it is ionic surfactant, then SDS, and some aliphatic alcohol, then only this is formed. So for type 4 Windsor system to occur, we have to fulfill certain conditions. So the conditions are these. Okay, so this could be treated as a screenshot for this entire Windsor systems. So type 1, 2 phases, type 2, 2 phases, type 3, 3 phases, and type 4, it comes down to one single phase. Alright, so now having understood these Windsor systems, so our last topic of today's discussion is now what are the different conditions that can govern or that can affect this type 1 and type 2 or type 3 Windsor systems. Obviously, as I talked, that it depends on the conditions, that means the choice of the surfactant and some ambient environmental condition. So let's take a quick look on that, and also we're going to take a look that how the structure of the surfactant is essential to govern whether we have an oil in water microemulsion or water in oil microemulsion. Alright, or we can have a simple micellar solution. So let's erase this one and let's take a look to those factors. So there are a few general factors that govern the Windsor systems. So these are obviously the nature of the surfactants, the electrolytes, and whether we are adding any natural electrolytes like sodium chloride, whether we are increasing the salinity of the medium. And those electrolytes actually become the governing factor when the added surfactants are ionic in nature. And also we have pH of the medium, and then temperature, and temperature is most pronounced when we have some non-ionic surfactants, and of course whether we add aliphatic alcohols or not. So that also dictates the Windsor systems, as we have already seen in case of type 4. So today we will briefly discuss about the temperature effect. So if we have a non-ionic surfactant, then at normal temperature, usually it would produce, you can understand, it is producing type 1 type 1 Windsor system. All right. And if we increase the temperature gradually, so this type 1 system would first change into type 3, and then it would finally settle into type 2 system. Alright, so therefore temperature plays a big role for the non-ionic surfactant. And the most important effect is the nature of surfactant, and there are several factors on the nature of surfactant. Firstly, whether we use ionic or non-ionic, but the most important of them all is the CP, that is the critical packing parameter. So remember, we have already discussed this critical packing parameter when we talked about surfactant micelles. So next we will see how this critical packing parameter would dictate that whether we will have a water in oil emulsion, microemulsion, or oil in water, microemulsion. And that would also, in a way, it would dictate the Windsor systems. So I guess we would like to stop it here, and we will address how CPP governs the microemulsion systems in the next lecture, lecture number 16. So please follow these video lectures, and I'm going to share one document describing these Windsor systems with you electronically. So please stay put and stay safe, and I will see you in the next lecture, lecture 16. So till then, goodbye.